In this episode, we take a practical look at how you can spot and test for biased data inputs in an AI system without needing to be a statistics expert or a machine learning specialist. A lot of beginners assume bias testing is something only mathematicians can do because they picture complex formulas and advanced graphs. The truth is that many of the most important checks are simple, human-readable comparisons that focus on who is represented in the data, how labels were created, and whether the data quietly favors some groups over others. If you can ask careful questions, read a few summaries, and think clearly about fairness, you can find the majority of problems early, when they are still fixable. The goal here is not to turn you into a data scientist, but to give you a reliable, repeatable way to pressure test data inputs so that an AI system does not inherit unfairness from the past and then scale it into the future. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To keep this approachable, start with a plain definition of what you are trying to catch. Bias in data inputs is a pattern that makes the data reflect the world unevenly, so that the model learns uneven lessons and then performs unevenly across different groups or situations. Sometimes that unevenness is obvious, like a dataset that barely includes older adults, rural communities, or people who speak with certain accents. Other times it is subtle, like a dataset that includes everyone but measures them differently, such as better documentation for some groups and poorer documentation for others. The key idea is that bias often enters before any modeling happens, through choices about what data to collect, how to clean it, and how to label it. That is why you can test for bias at the input stage, even before you look at model outputs, by checking representation, measurement, labeling, and proxy signals. This kind of testing is less about calculating a perfect fairness score and more about identifying risk signals that demand fixes or stronger controls. The first practical test is a coverage check, which is simply asking whether the dataset includes the kinds of people and situations the system will face in the real world. Coverage is about breadth, not precision, and you can do it using counts and categories rather than advanced statistics. For example, if the system will be used across multiple regions, the dataset should include those regions and not be heavily dominated by one area that behaves differently. If the system will be used on different device types, the dataset should include those device types and not assume that everyone uses the same hardware or network conditions. If the system will be used year-round, the dataset should include seasonal variation and not only one time period that had unusual conditions. When coverage is missing, the model often fails in exactly the places the data did not include, and those failures can land harder on groups already underrepresented. A beginner-friendly way to summarize coverage risk is to ask what populations and conditions the data does not seem to contain, and what harm could happen if the system performs worse there. After coverage, the next test is a balance check, which asks whether some groups are present, but so rare that the system will learn them poorly. You do not need a statistics deep dive to understand that if one group has 10,000 examples and another has 50, the model will usually get much better at the first group. Even if you do not know the exact thresholds, you can still identify extreme imbalance and treat it as a warning sign. Balance also includes the idea of label balance, meaning whether the outcomes in the dataset are distributed similarly across groups. If almost all negative outcomes appear in one group, you need to ask whether that reflects reality or reflects bias in labeling or prior decisions. Beginners sometimes get stuck thinking fairness means equal numbers everywhere, but that is not always realistic. What matters is whether the imbalance is explained and justified, and whether the team has a plan to avoid punishing the rare group with high error rates. If a team cannot explain why a group is rare in the data, that is usually a sign that the data was collected in a way that excluded them. The third test is a consistency check on how the data was recorded, because biased data is often biased by process, not by intent. Think about two employees doing the same job. One has a manager who documents performance carefully, the other has a manager who rarely writes notes. If a model is trained on those notes, the employee with fewer notes can look like an outlier or a low performer simply because the record is thin. In many datasets, Some groups have cleaner, richer records because they interact with systems that capture them more completely, while other groups have gaps due to language barriers, limited access, or different patterns of use. Consistency checks look for systematic missingness, meaning missing fields that cluster in certain categories, not just random blanks. You can also look for different definitions being used in different places, like one office labeling an incident as severe while another labels the same kind of incident as moderate. When recording practices differ, the model learns those differences as if they are real differences in people, and that is a classic way unfairness sneaks in. Now move to labels, because labels are where bias often becomes baked into the dataset. A label is the outcome the model is trying to learn, like approved or denied, suspicious or not suspicious, high risk or low risk, satisfied or dissatisfied. If the label is derived from a human decision, you have to ask whether that decision was consistent, whether it was influenced by stereotypes, and whether it had uneven enforcement. For example, if a dataset labels behavior as suspicious based on who got investigated historically, then the label may reflect where investigators looked, not where wrongdoing actually happened. If a dataset labels employee performance based on supervisor ratings, those ratings may reflect favoritism or cultural bias rather than true performance. A beginner does not need advanced math to see that if the label itself is biased, a model trained on it will repeat that bias with more speed and confidence. One of the simplest label tests is to ask how the label was created and whether it was audited or calibrated for consistency across teams. Proxy variables are another big risk area, and you can test for them with reasoning and a few sanity checks rather than complex correlation analysis. A proxy variable is a field that stands in for a sensitive trait without naming it directly, such as a zip code standing in for race or income, or a school name standing in for social class. Proxies are dangerous because people may falsely believe the system is fair just because it does not include explicit protected traits. A practical proxy test begins by listing what traits would be sensitive or unfair to base decisions on, then looking at the dataset to see what fields could indirectly represent them. You can also ask what the model is likely to learn from each field, because the meaning of a field is often richer than its label suggests. If a dataset includes a field for gaps in employment, that might reflect caregiving responsibilities that disproportionately affect certain groups. If a dataset includes language proficiency scores, that could become a proxy for national origin. The test here is not to prove the proxy mathematically, but to identify fields that deserve extra scrutiny and guardrails. Another accessible test is a plausibility check, which is basically asking whether the dataset tells a believable story about the world. If the data suggests that one group has dramatically higher rates of negative outcomes, you should ask whether that aligns with trusted external knowledge or whether it could be the result of measurement or enforcement differences. In a security setting, if one department appears to generate far more incidents, is it because that department is riskier, or because their systems log more events, or because they are monitored more aggressively? In a customer setting, if one region appears to have far more complaints, is it because service is worse there, or because the complaint channel is easier to use in that language, or because expectations differ? Plausibility checks push you to ask what alternative explanations exist for patterns in the data. This matters because biased datasets often look plausible at first glance, but the plausibility is a product of hidden processes, not true differences. You should also test for selection bias, which happens when the dataset includes only the people who made it into the system, not the people who were kept out. This is common in areas like hiring, lending, admissions, and even security investigations. If you train a model on successful applicants, you are training on the group that passed a past filter, which means the model may learn the filter rather than learning potential. If you train a model on reported incidents, you are training on what was noticed and reported, not necessarily what happened. Selection bias can make a model look accurate because it performs well on a narrow slice of reality, while failing on the broader population it will affect. A beginner-friendly way to test for selection bias is to ask who is missing because of earlier gates, and whether those missing people matter to the decision being made. If the system will be used earlier in the pipeline, the training data should reflect that earlier stage, not a later stage that already filtered people out. Another practical input test is a drift and staleness check, because bias risk changes over time as society, policies, and behavior change. A dataset from 5 years ago can encode outdated norms, outdated products, and outdated enforcement priorities. If a company changed its hiring practices to reduce discrimination, a dataset from before the change may still carry the older pattern, and a model trained on it can pull the organization backward. If a community experienced a major event that changed behavior, older data may misrepresent current reality. Drift and staleness checks are not about fancy time series analysis. They are about ensuring the dataset spans the right time window and that there is a clear reason the chosen window is acceptable. If the data is old because it was the only data available, that is a risk that should be documented and mitigated, not ignored. Bias testing includes asking whether the historical period captured is fair to the people who will be judged today. A key part of bias testing without statistics is making sure the team can produce simple summaries that anyone can understand. You can request basic distributions, like how many records exist in each key category, how many missing values exist in sensitive adjacent fields, and how outcomes are spread across those categories. You can ask for examples of records and labels, because seeing real samples often reveals inconsistencies that numbers hide, such as vague notes, mixed definitions, or labels that seem to depend on who wrote them. You can also ask for the data dictionary, meaning the plain language description of what each field means and how it is collected, because unclear definitions are a breeding ground for bias. When teams resist providing simple summaries, it can be a sign they do not understand their own data well enough to trust it. A beginner can be effective here by insisting on clarity and transparency rather than accepting confident language. It is also useful to check whether the dataset contains sensitive information that is not needed, because unnecessary sensitive fields increase both privacy risk and bias risk. If a model can achieve its goal without fields that relate to protected traits, then including those fields raises the chance the model will use them in ways that create unfair outcomes. Even if the model is not supposed to use them, their presence in the dataset creates temptation, future misuse, or accidental leakage. A practical test is to ask for a justification for each sensitive or sensitive adjacent field, framed in purpose language rather than convenience language. If the team says they included it because it might help accuracy, you can push back by asking what harm it could cause and whether a less risky substitute exists. Removing unnecessary fields is one of the simplest and most effective ways to reduce bias risk at the input stage. It also forces the team to think more carefully about what they truly need to accomplish the task. Finally, remember that bias testing is not a one-time event because new data arrives, new sources get added, and the environment changes. The point of learning these simple tests is that you can repeat them regularly and compare results over time. If coverage improves, balance changes, or labels shift, those are signals that need investigation because the model's behavior will follow the data. Bias is not only about whether the model seems fair today, but whether the pipeline that feeds it is designed to stay fair as conditions change. As you build comfort with these checks, you will start to notice that the strongest bias defenses are often organizational habits, like clear definitions, careful documentation, and routine review, not just clever algorithms. When you can test inputs in plain language, you can make responsible AI oversight practical, scalable, and understandable to the people who rely on the system.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.